All right, so for number of siblings example for this class, we're going to make our 3-column data distribution table where number of siblings is our variable, number of siblings, the frequency will be our second column, and then relative frequency will be our third column. So we've got 0, 1, 2, and 3. Is that it for this one? So how many people had 0 siblings? Nobody. Okay. How many people had 1? How many people had 2? And then 3 had 3? Okay. All right, so then to calculate relative frequency, does anybody remember how we did that? Relative frequency? Divided by the total. So the total here would be 2, 4, 7. So obviously if there's 0, that would be a relative frequency of 0. And then 2 divided by 7, and we'll take 3 decimal places. If you do 2 divided by 7, round to 3 decimal places. 0.286, thank you. And then we'd have the same. All right. So our relative frequencies should always add up to what? 1. Right, since we're dividing the part by the whole and then we're adding those all together, that would always equal 1. So we have our new definition here, random variable. A random variable is a quantitative variable whose value depends on chance. So because the number of siblings varies from student to student, it is a variable. And suppose now that a student is selected at random, then the number of siblings of the student obtained is called a random variable. Because its value depends on chance, namely on which student is selected. To represent variables, we use lowercase letters. Just plain old variables, we use lowercase letters, whereas for random variables, we use uppercase letters. For example, we would use lowercase x to represent the number of siblings, but we would use a capital letter X to denote the random variable number of siblings. So each one of these values is a value for the lowercase letter x, but the phrase number of siblings, that is our random variable. So some other examples would be for random variables, the number of students in a class, the number of children in a family, the number of cars entering a car wash in an hour. So why do we use random variables? So as soon as you calculate outcomes, you can do a bit more math on the outcomes and use more mathematical analysis, analysis on the outcomes. So then at the bottom here, important to note, 2 more definitions, probability distribution and probability histogram. Again, these are going to look very familiar. Very similar in appearance to our relative frequency distribution, which is this guy right here. This is a relative frequency distribution. And a Relative frequency histogram. What comes to mind when I say histogram? What kind of chart? Uh-huh. What comes to mind when I say histogram? What do you picture? What is a histogram? Yep, bar graph, but the bars are touching. So, histogram. And this time, though, the bars are representing probability. Determine the probability, refer to the sibling example. Let X denote the number of siblings on a randomly selected student. So determine the probability distribution. So for that, we have the number of siblings and these are variables, or these are values for the lowercase letter x. And then we're going to say, what is the probability that any random number of siblings would equal the lowercase letter x? What is the probability that if I choose a random person that their number of siblings would be equal to the ones listed in the left side of this chart? And we only have 0, 1, 2, and 3 for this class, to make it easier. So probabilities are actually going to be equal to the relative frequencies. So we flip back. We have 0, 0.286, 0.429. And there's your probability distribution. And next we would make our histogram, probability histogram. On the x-axis, we need to indicate that the 0 is not where it should be. It will be slightly to the right of the origin. So we're going to actually put 0 out here. And then we just need 1, 2, and 3. Along the y-axis, we need our probabilities, which we see at 0.429 is the highest, so we need to make sure it goes up to 0.45 at least. So we'll start with 0.05, just made it. So for 0, well, we don't need a bar there because it's 0, and then 0.286. So we're going to need to go up to nearly 3. And the same for 2. And then 0.429. And there's your probability histogram, but it needs some labels. So the x-axis, we should label number of siblings. And your y-axis, we would label probability. So then the note, and this is what you've already observed, the number of siblings is a variable of finite population, so its probabilities are equal to its relative frequencies. And then your gray box here says the sum of the probabilities of a discrete random variable for For any discrete random variable, capital X, we have the sum of all the probabilities where X, the capital X equals lowercase x is equal to 1. And then there's this notation. It says the sum of probability X equals lowercase x represents adding the individual probabilities. The probability that X equals X for all possible values X for a random variable X. Okay, great. We probably could have figured that out without the note. But there you go. That's 5.1. Now on to 5.2, expected value. One thing I want you to keep in mind as we talk about expected value is actually the same for our purposes as the population mean. Okay? It has a different, a little bit of a different process to calculate the expected value, because we can calculate expected value with a slightly different given display of information. So just keep in mind expected value and population mean, for our purposes, we're going to say those are the same. And that's why you see, recall from Unit 3, we have this formula for population mean. And if you want to remind yourself that mu, that's how you say that, mu is the population mean, you may not need to remind yourself that because it has already sunk in deep into your brains. That is the population mean. And then this is the sum of all the X values divided by the number of observations. So now we will apply that to a random variable X. Student ages. Can I volunteer to read student ages? Thanks.
Consider a population of 8 students whose ages in years are those given in Table 5.8. Let X donate the age of a randomly selected student. From a relative frequency distribution of the age data in Table 5.8, we get the probability distribution of the random variable X shown in Table 5.9. Express the mean age of the students in terms of the probability distribution of X.
Excellent. Okay, so we have some college students here with some ages. The population is 8. It's a very small population, artificially small, most likely for the purpose of us understanding this new phrase, expected value. So when we look at this probability distribution here, we can calculate the expected value by multiplying the value of the variable, or the age, times the probability of getting that value, times, I'm going to put parentheses, I like parentheses better, 0.25. And then adding that to the next value of the variable, 20, times the probability of getting that value, 0.375. And then adding on 21 times 0.25 and 27 times 0.125. And so then you can do that calculation real quickly in your calculators. What'd you get? 20.875. Anybody else?
Yeah.
Great. So about 21 years is the age. The expected value. So let's go ahead and kind of check that with the method that we're used to, which is just adding them all up and dividing by how many there are. So we are given this data set with each individual observation, which we won't necessarily be given that information. When you're looking at a population of size 500, this is not as practical. But like I said, since we only have a very small population, we can do this pretty easily to calculate the population mean, adding up all the x's and dividing by how many there are. And what'd you get when you did that, Gigi? Same thing. So you can see, I wasn't making it up, they're the same. And you can see that described here with this fancy notation. I like to look over here. This is what the textbook says. And you can see, I like putting them side by side because you see that the population mean is in the same spot as the notation for expected value. So they're interchangeable. And you see here also, it's nice because the different elements are actually defined. So you, it kind of indicates multiply each value by its probability. After you multiply, then you add them together. Okay, so that's something that can get confusing. Okay, so do I add these all up and then multiply? The order can be confusing just by looking at that. But so first you multiply and then you add them all together. So we'll do a little practice problem here. Busy tellers. Can I get a new volunteer to read busy tellers? Madeline. Thanks, vocalist, for volunteering.
Prescott National Bank has 6 tellers available to serve customers. The number of tellers busy with customers at, say, 1 p.m. varies from day to day and depends on chance. Hence, it is a random variable, say x. Past records indicate that the probability distribution of x is as shown in the first 2 columns of table 5.10. Find the mean of the random variable x. In other words, find the expected value of x.
Okay, great. Thanks. So over here, we have our probability distribution. So we have this random variable. What does the random variable represent? That's kind of the key thing to identify first as you are working on problems like this. What is the random variable that we're talking about? If you look at the caption, it tells us pretty clearly the random variable is the number of tellers busy with customers. So at any given time, say 1 p.m. So we look at the table here and we look at their different probabilities. And then we look at the probability of getting the value times the value, and we have each of those listed, and then they're added together for us. So what is the expected value for the variable? Exactly, 4.118. Or approximately 4 busy tellers at any given time. All right, so that's kind of a brief overview of the 2 topics. Hopefully you feel pretty confident about being able to calculate expected value, as well as feel familiar now with the phrase random variables that allow us to quantify different processes and display probabilities and distributions, as well as histograms.